Hello everyone, I'm Gauri, and today I will be talking about the project I did over the summer with my mentors Professor Finney and Dr. Lu. It's about stream intersection and tidal disruption events. Now, what is a tidal disruption event? When a star passes by really close to a black hole, the tidal forces of the black hole have an effect on the star similar to how the moon affects the Earth, but it's much more exaggerated. The black hole squeezes and stretches the star into a very thin spaghetti-like stream that eventually follows the star's orbit and intersects itself or collides with itself. This is much more evident in this GIF over here, where you can see the intersection happening. Now it's important to note that this stream or this GIF is unrealistic because usually the stream has much higher energy, it's much more eccentric, and also different parts of the stream have different energies. But not all parts of the star have this fate. Some parts gain enough energy to escape, they're unbound. And the other parts, they eventually undergo relativistic precession, like in this figure, and they intersect with the previous fallback stream. We have to find where this intersection point is. That's the aim of this project. But why is this so important? Why do we need to find these intersection points? Well, on intersection, there is a shock. This shock is observable and it leads to an envelope of expanded gas. Some parts of this gas, they have low enough angular momentum so that they eventually form an accretion disk around the black hole. This accretion disk is important because it can help study various properties of the black hole, and it's observable in all parts of the electromagnetic spectrum. Some parts of the stream, they approach too close to the black hole and they plunge in. But it all starts from this intersection point. Now, how will we go about computing it? Eventually, we are interested in the three-dimensional Kerr black hole, which is a rotating black hole. A is the spin of this black hole. In this case, since it's three-dimensional, we need three constants. But to simplify it, let's start with the two-dimensional case. The Schwarzschild case is the case where the black hole does not spin. The orbit is two-dimensional, and so we only need two parameters to decide what the orbit would be, and that's the total energy E and the angular momentum H. Then we move on to a spinning black hole again, but in this case, the orbit is again restricted to two dimensions, and it's planar. Similarly, in this case also, we use the energy E and the vertical angular momentum H. Next, finally, we move on to the 3D Kerr case, where the orbits are 3D, and we introduce another constant, which is the Carter constant, which is basically a measure of how inclined the orbits are. Let's start with the Schwarzschild case. Now, in this case, the geodesic equations of general relativity will help us find how the orbit would look like. The equation, we can integrate these equations to find it. Let's look, for example, at the equation for r dot, or how r changes with proper time. This is expressed in terms of the energy and the effective potential that is plotted here. We can see that when E squared minus V effective is 0, that is when r dot is 0. And that gives us the maximum and minimum values of r, or the bounds of this orbit over here, or over here. We can, from the effective potential, we can find other more interesting orbits. For example, if you're at the peak of the h equals 4 potential, or the angular momentum equals 4 potential, we get an unstable circular orbit, which basically, if you push the particle orbiting the black hole even a little bit towards the black hole, then it just goes plunging in. But if the energy is even a little bit different, for example, 1 versus 0.99998, that gives you a zoom whirl orbit, where the particle orbits the black hole in a circular orbit many times before it zooms off to infinity. Two very different outcomes with a very small difference in energy. But eventually, this is the case we're interested in, because we want to find what the stream intersection is. We can find this through symmetry, because this part of the orbit looks exactly the same as this part of the orbit. Or we can compute different points on these two intersecting orbits and see where where the difference between them goes to zero. And that will give you the intersection point. Next, once we have the intersection point, we can vary the angular momentum h and see how the intersection point varies. This would be useful because we already know the answer for the post-Newtonian limit. The post-Newtonian limit is when h is greater than a certain value. And that's because for larger h, the orbits are much farther out from the black hole, and relativity does not matter as much. The post-Newtonian limit is described by these equations over here, where through the semi-major axis A of the ellipse and the eccentricity E of the ellipse, we can find what the precession angle is to first order, and so we can find what the intersection point R is. Now we plot this analytically determined R intersection, and we also plot what we find our intersection to be. In the post-Newtonian region, or for this region, the plots match, which makes sense. And for the region that is the relativistic region, they start to diverge, which would happen because relativity takes over and Newtonian physics can't still be used. Then we move on to the equatorial Kerr case, or the case of a spinning black hole, where the orbits are two-dimensional. In this case, also, we follow the same methods as the Schwarzschild case. It's very similar. We have an equation for R dot that is described in terms of V effective. V effective is plotted over here. Now, we can again find what the turning points are, or the pericenter, the closest approach to the black hole, and the apocenter, the farthest point from the black hole, and integrate the geodesic equations given to find this orbit. Similar to the Schwarzschild case, we can get other interesting orbits. For example, when the black hole spin is oriented opposite from the angular momentum, the black hole tries to orient the orbiting particle with itself when the particle is too close to the black hole. This is why you get this flipping back phenomenon, which is very interesting. But eventually our goal is to find what these intersection points are, which we do in a way similar to the Schwarzschild or non-spinning case. Once we have our intersection, again, we want to plot it as a function of angular momentum h. Now, we do this for different black hole spins A and for different energies. If you look at this plot and think about it, it makes sense that our intersection versus h, the different plots approach each other for the Newtonian region and are very different from each other in the relativistic region, because in the Newtonian region, black hole spin, or A, has no meaning, and neither do black holes. Relativity does not matter. And so you wouldn't expect the black hole spin to have any effect on these plots in the Newtonian region. They all are the same. But in the relativistic region, A starts to matter as you get closer and closer to the black hole with smaller and smaller angular momentum. In this case, we can look at the behavior of our intersection for different black hole spins. Now we move on to plotting our intersection as a function of angular momentum for different energies. Now, as you can see, the plot here is very different from the plots we got earlier. Because in this case, in the relativistic region, they match each other. But in the Newtonian region, they start to diverge. Now, this gives us hope because this tells us that the single energy approximation, that is each point of the stream has the same energy, that approximation makes sense because changing the energy is not changing our intersection by that much. And this is only in the relativistic region. In the Newtonian region, however, it is important to consider what the energy would be and to consider that different parts of the stream would have different energy. Now we are ready to move on to the three-dimensional case, or the general Kerr case with a spinning black hole and three-dimensional inclined orbits. Now this is very different from the Schwarzschild and equatorial Kerr cases because in this case, there is no guarantee of intersection between the first and the second orbit. That is, there can be many orbits before intersection happens. If the streams were just lines, intersection would never happen because they would always grow apart from each other as the inclination angle theta changes. Theta here is a measure of how inclined those orbits are in 3 dimensions. But if they were lines and they can't intersect, what makes them intersect? They intersect because in reality, the streams have a certain width. This width is called h. When the sum of their widths is more than delta S, or the separation between the centers of the streams, then you can tell that intersection would occur because the two streams would overlap and there is the collision. But how do we find delta S and how do we find H1 and H2? Well, first we project this 3D orbit into 2 dimensions. We see where r and phi are equal, similar to how we did for the 2-dimensional cases. And then for each of these intersection candidates, we see what their inclinations of those two intersecting orbits are. And from those inclinations, we find what delta S, or the proper distance, is. It's useful to note here that I1 and I2 represent the number of orbit that's intersecting. For example, this is I1, this is I2, this is 1, this is 2, this is 3, this is 4. And that's how you mark the orbit by a number. So we can see that we draw up the first few intersection candidates, or the first few points where the streams could be close enough to intersect. Now we just need to find delta, the different stream widths. We already found delta S. But for this, we need a model for how the stream thickness evolves. If we have an initial value for the stream thickness at apocenter, where we start, and we have an initial expansion velocity for that stream, which we get from the escape velocity of the star at pericenter, we can find how the stream would evolve. Now, this is the most poorly understood part of the model, and that's because in the last few days, our expectations for the evolution changed. People previously thought that the stream evolves according to the Newtonian tidal force equation, and shocks happen at pericenter. But we found through our simulation that shocks don't have to occur at pericenter. In fact, they don't. They occur initially very close to pericenter, and slowly they can occur farther at random locations. But they don't always have to occur at pericenter. And that's because the location of the shocks is when the stream width is 0, and stream width does not always have to go to 0 at the pericenter. This means that, so if the stream width is not 0 at pericenter, this means that the symmetry that existed in the Newtonian case was broken. This was because the two ends of the stream, they precessed, and they did not meet again at pericenter. Once we have this model for stream thickness, we can see if collision occurs or not. This plot can be read by starting here at apocenter, going towards pericenter, and following this plot for the thickness. Then we go from pericenter to apocenter, and then we go back to pericenter. Now let's look at the first few intersection candidates and see if collision is occurring for them or not. The first and second half orbit at 367, R of 367, the distance between them is around 14, but the width of the stream at those points is on the order of 2. And those widths cannot sum up to 14, and so no collision occurs. Now let's move on to the collision point and see how we find that collision occurred over here. Well, if you zoom in the place over here, you can see that the thickness of the first intersecting half orbit is around 0.15, and the thickness of the second one is around 0.25. If you add h1 plus h2, 0.15 plus 0.25, you get 0.4, which is of course higher than proper distance, 0.29. Since h1 plus h2 is higher than delta S, we have a collision, and that's the answer. This is the collision. We can do this for any parameters because this is the same code, and so the next steps would be to do this for a range of parameters in parameter space and seeing how this collision point would vary. I couldn't have done this or found the collision point without the guidance of my mentors, despite it being a very challenging online format, and my friends who helped me with programming and math along the way, and of course the CERT program stuff. Thank you, and I hope you have a lot of questions in the upcoming Q&A session.